So let's talk about polyprotic acids. And an example of a polyprotic acid, or a polyproton acid, if you will, is ascorbic acid. Now I have here the molecular formula of ascorbic acid, and you see that there's this H2 in red. Those two protons are acidic protons. They are carboxylic acid protons. You can look at the structure of ascorbic acid in the book. In the polyprotic section, they have the structure of several polyprotic acids. And the two different, because it has two acidic protons, it has two Kas. It will first lose one of the protons, and then in a second equilibrium, it can lose the second. Okay? So losing the first proton has a Ka of 8.0 times 10 to the minus fifth. If we then lose the second proton, it has a Ka of 1.6 times 10 to the minus 12th. And you'll notice that Ch16H6O6 appears in both equations. It can act as both a base going this way and as an acid, meaning that this is an amphoteric species. So the question is, what is the concentration of C6H6O6 2 minus in a 0.1 molar solution at equilibrium? In other words, how do we take both equilibria into account in order to find answers relating to the overall system? Okay, well, what we need to do is, because we have two equations, we need to have two iceboxes. So, how do we solve this question? Well, let's go for it. So, let's say we have a 0.1 molar solution of our ascorbic acid. There's our initial ascorbic acid. Well, we know the first equilibrium is the first one's going to happen, right? Because we have an ascorbic acid solution, okay? So we always start with the first equilibrium and we figure that answer out for that, and then we move on to the second equilibrium. So to solve this for the first equilibrium, it's the icebox, as we've been talking about all chapter long, and for two chapters really. And so we can solve for x. We can assume x is negligible. We can solve for x doing that, okay? And we then have to check our assumption. It is 2.8%, which is less than 5%. So our assumption is all good. Therefore, the concentration of our conjugate base, H6O6, is 2.8 times 10 to the minus third. Also, our concentration of H3O plus from this equation is 2.8 times 10 to the minus third, because both of these different species have a final concentration of X. Now, we can bring both of those guys forward to our next equilibrium. So we found out from our first equilibrium what the initial concentrations of both of our species are for our second equilibrium. We know that our concentration of our 2 minus ion is 0 because we haven't made it that far yet. So then we have another icebox equation, but now, of course, because we have two different initial non-zero concentrations, we have two different expressions, okay? And we get this Ka expression for the second reaction. Now we can once again assume x is negligible, getting rid of this plus x and this minus x, okay? Then solving for x, we get 1.6 times 10 to the minus 12. If we check our assumption, we find, yes, indeed, that is way below 5%, so we're okay, assuming x is negligible, okay? And therefore, the concentration of C6H6O6 is 1.6 times 10 to the minus 12th, because it is equal to x for the second thing. So the general trend is, when we have a polyprotic acid, we first deal with one equilibrium, and then we use the answer from the first equilibrium to move to the second equilibrium.